I don't know, I guess we should start. I see that Nicholas is out of office today, so probably he won't be joining, and I'm not sure where is others. Should we start? Or should we wait?
Maybe half a minute, just to be sure.
Okay, let's wait another minute. I guess we should start. Right, so we are talking today about second chapter called compilation. And maybe we can, just like three of us right now, so we can maybe share our experience of reading this paragraph. I don't know, for me it was a bit more difficult than the first one because there was more code examples, and they were in this really assembler looking language. I don't know, like these YARV tokens. And but it was quite interesting, and I've actually one interesting thing that I've googled after reading this chapter that there is this option supports jog into YARV apparently, and when you actually it's allow you to get this go to blocks in Ruby, but as well it also have like two jogs. So if it adds the variable called like answer to everything, and it's just like the variable will be 42, like the meaning of it. And there is another one which actually produce like some sandwich with lettuce and bacon, like two jogs into the interpreter. But I still kind of didn't understand, is it actually so with this new compiler edited into Ruby 1.9 like and up, like, but Ruby is still the interpreted language, right? Or am I mistaken?
I think it still is an interpreted language.
It just like, I just feel that like this compilation, it's like the name is a bit misleading, because even in the book, the author says that even when after like translating everything into YARV directives, it's still not basically you can't like it's still interprets then. that. Hi, Eric. We are discussing the second chapter of the book, and we are discussing if adding YARP into Ruby in 1.9, does it makes Ruby compiled language? Looks like not, but it's a bit confusing.
It will be both. It's a little confusing. So typically when it uses a bytecode compiler, it's both, because it uses well, in case of Ruby, it's a little confusing because it doesn't save the bytecode. But if you take Python, for example, which does, it's interpreted in the sense that as it runs, it will translate that bytecode to, machine code basically. But it's compiled because it has this distinct compilation and execution step. But yeah, it's a bit up to personal interpretation, I think.
Okay. Yeah. So I guess it will be kind of like be strange to read. I don't know any articles when they'll put Ruby into interpreted languages section, but right now it's kind of yes and no.
At least my approach to usually is like, if it has a VM, I just consider it interpreted. If it doesn't, like let's say Go, for example, then it's compiled.
And what's about Java, for example? It uses bytecode, but it's still a compiled language.
Yeah, it's kind of in a similar area. It's, I think, even more confusing because it has a just-in-time compiler. So as it runs, it will translate your Java code into machine code and then just use that. Sometimes people use like combinations of terms. So they say like, oh, it's a bytecode interpreter, or a just-in-time compiler, but it's actually an interpreter, things like that. So this is basically different terms, and they mean the same thing.
I had a question here about, because I'm a little bit more familiar with Python at this layer, and wondering, why Ruby doesn't have RBC files. Like Python has PYC files, which is the compiled bytecode cache to disk. Yeah, I mean, like, I think from what I understood, it's like it compiles and holds it in memory. I guess for most Ruby applications, it doesn't really matter, but maybe for a script that you're invoking many times, then it has to do this recompile every time. Whereas Python, maybe there's a small performance benefit by having the bytecode precompiled on disk, and if the script hasn't changed, it will just use that bytecode. So I thought that was kind of interesting, and I've wondered like whether this is something that will ever change, or whether there aren't like that many performance benefits for doing it.
It mostly affects the startup time.
Yeah.
The thing though, there is with Ruby, there isn't really a clear distinction of startup time, because as it runs, it may load additional files and such, and as such is really hard to define. When is the application started versus sort of when's. I guess you could measure like sort of time to first byte on a web page, like time to first Ruby line, essentially. I think it would help. It kind of depends on how fast the compiler is already. So as far as I know, for example, the Ruby bytecode compiler doesn't really do many optimizations. It has a few basic ones, but it certainly doesn't have any optimizations that take a certain amount of time to process. And so it's entirely possible that because of that, using a bytecode cache wouldn't give that big of a speed up. Certainly, I wouldn't expect like a Rails app to suddenly be X% faster or something like that. I would say you're going to see this more in programs where they require a lot of files, for example, especially big files. And so you mostly see this in like, command line scripting, for example. There is the added benefit, if you compile the bytecode, you can theoretically get rid of the source code and just ship the bytecode, which may or may not take less space. But I think, again, for most people using Ruby, disk space is not really a concern. Like these bytecode files certainly don't get gigabytes in size. It's 5 megabytes maybe for like a Rails app, for example. A Rails app might be a bit more, but not a whole lot.
One funny anecdote, I was at a talk where at a Python conference where a developer of someone who wrote a disassembler for Python bytecode, basically converting Python bytecode into something you can read. And he said the #1 application for this was someone who accidentally deleted their Python script, and all they had was this PYC file, and it's been through like generations of employees, and they have like, it's like some critical component, and they said like what they use is the disassembler to make changes to it, because like and I think that's a common thing actually in Python, where you accidentally delete your Python script and you're left with a bytecode file, and that's all you have. So it's funny.
Yeah, I think for Ruby, at the end of the day, it's probably a mix that compiler probably is fast enough, probably because it does very little. And I think the sort of heritage from Ruby 1.8, when it was an AST interpreter, difference there is basically it will parse the code into a syntax tree and just interpret that directly without any bytecode in the middle. That's probably why they don't have it today. I think just to add there, I think JRuby is in a similar sense where they don't store their own bytecode, and that's mostly because they compile directly to Java. I do think JRuby has the ability to spit out some form of Java output. Not sure if it's like a Java class file or like a jar that you can then run. And Rubinius has and still does, similar to Python, where it produces bytecode. And I think basically any new interpreted language with bytecode will do it separate, similar. Like Erlang and Elixir also do it, where you have this distinct compilation and execution stage. And I think, let's see what other new languages are there. I think Lua might be an exception to that, where they also compile it in memory. But I think that's also the use case where Lua is often embedded, and they might not have a file system, or maybe like if it's in a video game, might not have access to it. I think Lua JIT does the same thing for that reason. So it kind of depends or varies per use case.
But like if we're like talk about MRI, so like this bytecode which is compiled, it's like, as far as I understand, it's stored somewhere like in the cache, and when like the program is like killed, it just deleted, because when you like change the program, you'll have to like do all this tokenize parsing and compiling again, so we'll need like new files for bytecode, right?
Yeah, so the best way to sort of envision that is, I would imagine like how most do it is you basically have like a giant hash map which says, for this file, this is all the the methods, the classes, whatever defined inside of it. And then for every one of those, it contains some info about the location, the number of arguments, etc., and the instructions to run, or the bytecode. And then when it wants to run a method, it will look it up through this database, basically, get the chunk of bytecode to run, and then it will typically sort of push that on its own stack. It's basically just an array, and then it will start running over those instructions. To sort of envision that, typically what an interpreter does, it's basically a huge loop with a big switch in the middle, and that switch handles every instruction. And then to run the code, they have a stack of methods or blocks of instructions basically to run. So when you call a method, it will just push on that, start running it, and then when it's done, basically pop and continue where it left off, etc. So it's not so much a cache in the sense of I don't know, what's like Redis basically. I mean, they don't use Redis, but things where things have like an expiration time and things like that. It's more like essentially a hash map saying this method has this list of instructions to run, and then when it exits, it just deallocates all the memory.
But is it stored somewhere on disk, or just like I assume it should be huge? Like, for example, if you start a GitLab application, so it's like this bytecode, like all these files, there should be like a lot of them. Like it should be like huge database. So it should be stored somewhere on disk, right? It's not in memory.
No, it stays in memory, and the size is typically not that big. This will of course vary a bit per language, but if you take, for example, GitLab's source code, it is, I'm probably not going to get like other stuff, but if you just the app directory is 90 megabytes, but that's also JavaScript. Let's say lib 50 megabytes. So let's say the whole source code of GitLab, just Ruby code is 100 megabytes. The bytecode is not necessarily a one-on-one representation. So for example, in a Ruby source file, if you refer to the number 10, 100 times, let's say 100 lines, that's 100 lines. And so 10 needs 2 bytes at the very least, and then you have 100 lines to process, 100 new lines, etc. But within the actual bytecode, it might see, hey, we refer to the same thing 100 times. Let's put that number 10 somewhere once, and then just refer to that. So there's some form of compression usually going on. It's not really compression in the sense of, say, gzip, where you take it, you actually squeeze it. It's more like when things are repeated, we store it in a common place and point to that, for example. But things like comments are not there. They're thrown away. You don't have white space, things like that. So the bytecode usually will be smaller, depending a bit on how much debugging information you include, for example. So a method might need to store the path to the file in which it was defined. And if a compiler is smart, it will see, hey, we refer multiple times to the same file, so we only store this once. But they may also not be. And then you end up with potentially this big file path being repeated a whole bunch of times. But so to give you a quick illustration, if, so for example, let me see. So for my own programming language, for example, the source code of the standard library is about 2 megabytes. If I have to see if I compile that, let me see, how do I do that again? It's a bit more difficult. Maybe I still have it cached because that might be a bit faster. Sorry, 1 second. Bytecode release. Oh, that's the old stuff. Either way, source code is like 2 megabytes, but I believe the bytecode is usually like 0.5 megabyte or something like that. So it's a fairly substantial reduction, and that's because things that are duplicate, it will try to reuse as much as possible. So file paths, integers, that sort of thing, strings also. And I would imagine Ruby does something similar to a certain extent. But it's entirely possible that for GitLab, I know, let's say it uses 1 gig of memory. I think it's like half a gig these days, but it's entirely possible that 50 to 100 megabytes of that is just bytecode.
Yeah, I asked it a question and then I realized we have like our modern computers with like a lot of memory. So even this like the process like takes 1 gigabyte or 2, just like, yeah, we have it. We can have so much data in the memory. It's not a problem.
Is there a Ruby implementation that compiles Ruby code to an actual machine code?
Not any ones that do directly. I think there have been some attempts in the past, but Ruby as a language is too dynamic. Like often when you look at the source code, you can compile it to machine code, but it's probably not going to be any particular more efficient than just using an interpreter. And so what JRuby does, and what Rubinians did before they removed the JIT, is they use a JIT compiler. And the way they work, they will typically sort of watch your, a method, for example, as it runs, and it will record perhaps what types of arguments are given to it. And then it might at some point say, hey, the last 10,000 times this method got called, all the arguments were integers, the output was an integer. So let's compile it under the assumption that that's what it takes as input and output. And then it can sort of try to optimize that. And then it usually has some sort of clause at the beginning where it says, hey, if the input is not an integer, bail out, go back to the interpreted code and throw away the compiled code because we made the wrong assumption, basically. I don't think there's anything today that does that before it runs. In Python, you have Cython, I think it's called. Python, but with a C instead of a P. And it takes, I believe, a subset of Python and will compile it into a Python C extension. But that's specifically meant for writing Python extensions. It's, as far as I know, not really something you could use without a Python runtime, for example. I think the closest today to compiling Ruby to machine code will be Crystal. But really the only similarity Crystal has with Ruby is that they share similar syntax. But sort of semantics-wise, they're completely different languages.
I just have really small comment about like that. I guess like in the future when Ruby will get even more new features, it will be even more difficult to create something like implementation that will be compiled into machine code, because like what we saw in this chapter that this keyword arguments, when it's compiled into YAR instructions, it took like even more lines to address it. It's even have like this if condition and so on. So probably like when we'll add even more dynamic features, it will be even difficult to do it in the future. So yeah, I guess it's.
Oh yeah, absolutely. Like the Ruby 2.7 does have a JIT, but it's by, from what I remember, very experimental. And in a case or in a state where it gives some benefits to some numerical benchmarks, but I believe Rails was even slower with it. I think for the long term, yeah, Ruby definitely needs it. I think languages like, implementations like JRuby have shown that you basically need that to make things go faster. And it's a bit of a recurring thing with any interpreted language. There's only so fast an interpreter can go, and it's usually not fast enough. at least for the case that people want to use it for. I think Lua is probably the odd exception, where the base interpreter is actually pretty fast. But then Lua JIT, for example, they have a JIT compiler, and they managed to be able to produce Lua code that can outperform the equivalent C code. And that's because when they JIT compile, they can compile it specifically for your machine, so they can use whatever functionality that might have available. Basically, all the work that you normally have to do to figure or to support code running on different architectures, you can just throw all of that away, because oh, we are running on this, so we only have to be concerned with that. But the Lua JIT compiler is basically written by compiler Jesus, so to speak. The identity of the person is unknown. The person goes by the name Mike Paul, but it's a fake name, and people don't really know who he is. But it's a really impressive piece of software. Like it's insane how fast Lua JIT can be. They of course made trade-offs. Specifically, it runs a few versions behind Lua, and the author at some point said, I'm done with it, because he was tired of having to catch up with Lua. Because the Lua developers would, as far as I understand, they like to change things left and right. So a new version would be announced, and it's like, all this stuff changed. In Ruby, they're a bit more conservative, so I think a JIT will be a little less painful. But Ruby also has the problem that as a language, it's much more dynamic compared to Lua. And not just that, people actually use it. So you pull in a gem, and chances are you will define a bunch of methods dynamically. And that sort of stuff is surprisingly difficult to optimize for. The JRuby people wrote about this quite a bit over the last decade or so. And they go through extensive trouble to make sure that if you redefine, say, the plus method on an integer, JRuby supports that, even if it means that performance will suffer as a result. But there's some stuff where they said, look, we're just not going to support this. In particular, there's the object space module in Ruby that you can use to traverse all live objects and do a bunch of other stuff. And I think JRuby does support that, but you have to start it with a certain flag. And even then, it will only support, I believe, a subset. And that flag has a pretty big performance impact. Yeah, Ruby absolutely will need a JIT for the next decade.
Will type signature help Ruby performance in some way?
To a certain extent, yes. So it helps in the sense that, let's for a moment assume Ruby was a statically typed language. At runtime, you don't have to figure out what the input and output is, because you know that. Assuming that this information is exposed to the runtime. Because a lot of languages, they don't. They throw their types away after compilation. And so, for example, what you could do is, if you have a let's say you have a loop over an array of integers, and inside you do another loop over an array of integers. You could turn that into a what's called a vectorized loop, where certain operations can be done in parallel at the CPU. And for Ruby, that's probably not what people use Ruby for. It might not be the best example, but that's a case where, because you have type information, you could perhaps even optimize that before your program runs. So as you compile the bytecode, you might say, oh, hey, we recognize this pattern. We know these are the types. So let's generate some sort of bytecode that's a bit more optimized. And so, yeah, it can definitely help. The tricky bit there is that because Ruby is dynamically typed, any type signatures you add on top are either going to be inaccurate, because people might forget to update them, or they're not going to be used everywhere. So you still need a runtime that can dynamically figure out what it's dealing with. And I do think, if these type signatures, if they catch on and if they stick around, we might see Ruby implementations perhaps use that as sort of a hint for the optimization process. But I'm personally a little skeptical about signatures sticking around. I'm fairly certain they will fade away. And that's because they've been tried in the past by different static analysis projects, mostly research projects. And sort of the recurring consensus was that unless it's part of the language sort of enforces it, people just forget about it. Or you end up with these libraries where people just don't want to maintain these signatures. So now there's perhaps an entire chunk of your program that you cannot type check. So it's one of those things we either need to go all the way or it's going to be a bit of a hit and miss.
Okay, it looks like the time of this meeting is over. Do we have anything else to discuss, or we can just run away? Okay, so if there is nothing else to discuss, so see you next week. So thanks, Jörg, for joining. It was really interesting to hear. So see you.